Okay, so we will start the class, okay? Is my screen visible?
Yes, sir.
Okay. So once again, good evening, everyone. So in the last class, we have discussed about shear force and bending moment diagrams for beams which are subjected to point loads, right? So in the last class, there was a bit of confusion regarding the sign convention for bending moment, right? Sign convention for bending moment, okay? So what I have said here, there is the top layer or the back layer or the left surface. If it gets contracted, then the bending moment is positive, right? That's the sign convention which we are following, right?
Yes.
Yeah. So once again, let's revisit what is that actually, okay? So if I have a beam like this, okay, imagine this is a beam, and let's say this is point A and this is point B, okay? So if I have a bending moment like this, say, for example, if I have a bending moment like this, then which surface actually gets contracted here when viewing from the front?
Left.
Right.
Right.
Yeah, right surface gets contracted here. So it means the bending moment due to this M is actually positive or negative?
Negative.
Yeah, right side gets contracted, okay? So bending moment is negative. And similarly here for this case, again same beam I am drawing, okay? Same beam, and let's say this is point A and this is point B, and now I am actually having a bending moment like this. You can imagine this bending moment, right? For example, this is yeah, you can imagine this bending moment, right? From the right plane, if you see, this bending moment will be visible, okay? So here when you are viewing from the front, which surface actually gets contracted?
Back.
Yeah, back surface. Yeah. So back surface gets contracted. So bending moment will be?
Positive.
Yeah. So now it's clear, right? What is the sign convention?
So you should all view it from the front only.
Yes, always we have to view from the front to get which surface actually gets contracted. Maybe for the bending moment sign, since it is here, it is not clear. I have to tell, like for the bending moment, you have to look from the right side plane like that. But when you are having questions regarding this, the directions will actually be very clear. Okay.
Okay.
Yeah. So next
So
today,
we always need to look from front.
yes, we always have to look from the front so that we can decide which surface actually gets contracted.
Okay, sir.
Yeah. So today we will do a small problem based on what we have learned earlier, and then we will proceed to uniformly distributed loads. Okay. So we will solve one question. I have a beam. Okay. And this is actually hinged at both the ends. And here I am having a bracket like this. Okay, and here it is acted by a load P, and this length is L by 4, and this length is L by 3, and these lengths are L by 2 and L by 2. Okay, let's take this point as A, then B, C, D, and E. Okay, so can you please draw the tensile load or the axial loading diagram, the shear force diagram, and the bending moment diagram for this beam?
Sir, P is outward load or inward?
No, P is an inward load. I have marked here, right? Using this arrow, okay? This is point E. Yeah, this is point E, and P is acting here, okay? So first, what we have to find here, whether everything is known or like you have to find the reactions.
Reactions.
Yeah, you have to find the reactions, right? So we will draw the bending moment, the bending moment diagram, the shear force diagram, and the axial load diagram for the member AC. Okay. So in order to first find the reactions, like the same system, I can actually describe by this system. Okay, if I am taking the AB as my member, okay. AC as my member, okay. So here I will be having some reaction, right? Here I will be at A, I will be having some reaction, and at C, I will be having some reaction. And whether can I use this P to act along this beam AC? How it will act actually? Due to this force P, okay. What force I will be getting at point B?
Horizontal force and moment.
Yeah, we will be getting an horizontal force like this, okay, acting at point B, and a moment, okay. Moment, what will be the value of the moment? It will be PL by 3, okay. I am denoting this moment by MB, which is equals to P into L by 3, okay. So now here we have like a net horizontal force and a net bending moment, okay, which is equals to PL by 3. So in order to find the reactions of this hinged support, what I have to do here, since summation, so I will be using the equilibrium equations, force equilibrium equations, summation V equals to 0 and summation M equals to 0, right? So using this, whether can I get the reactions here? Here summation V will be equal to RA plus RC equals to 0, right? Correct, right?
Yes, sir.
Yeah, so which means like both RA and RC are equal in direction. I mean equal in magnitude, but opposite in direction, okay? RA equals to minus RC. Then with respect to moment, whether can I find out, it's very difficult, right? Because like on both sides, maybe I have to take the force, or like I have to consider one side as, like for example, summation M. For example, if I take the moment about A equals to 0, then I can find out RC value, isn't it?
Yes.
Yeah. So what I will do here is, like, there is a shortcut for this. Okay. For example, here this actually we can use only when the condition is like this. For example, summation V equals to 0 and there is a net moment acting on the beam. Okay. When the condition is like this, then what I can use is, like, I can actually take the directions of the vertical reactions are equal and opposite, and then I will find the magnitude of the vertical reaction as, like for example, the magnitude of vertical reaction is equals to the net moment on the beam divided by the total length of the beam. Okay. So here, what is the net moment on the beam? It is actually PL by 3, right? Yes.
Yes, sir.
Yeah. So and the total length of the beam is actually L. Okay. So the magnitude of the reaction will be P by 3. Okay. And the directions of the vertical force or the reaction should be in such a way that it is opposite to the direction of the net moment. For example, we have already said the net reactions or the vertical reactions will be equal and opposite in direction, right? From this case we have said. Yes. So here, for example, the moment is acting towards this direction. So the net reaction should be in this direction. Okay. So RA will be equal to P by 3. And here, since it is acting in this direction, so the reaction should be towards the downside. RC equals to P by 3. Okay. Is this clear or should I have to explain it further?
Sir, explain it.
Yes,
Okay.
okay.
Okay, I will explain it now. See, for example, up to this it is clear, right? How I am calculating the magnitude of the vertical reaction when only concentrated moments are acting, okay? And if summation V equals to 0, then you can use this method, okay? Magnitude of vertical reactions is equals to net moment on the beam divided by the total length of the beam, okay? So the net moment here acting on the beam is actually PL by 3. And dividing it by the length of the beam, which is here in this case is L. So I am getting the magnitude of the vertical reactions as P by 3. Okay. And these reactions should be equal and opposite in direction. Okay. So how I'm actually choosing the direction is, for example, the direction should be chosen in such a way that it is actually opposite to the direction of the moment direction. Okay. For example, when you are looking only AB, okay, only AB part, if you are looking, the moment is actually acting towards this direction, right? So the reaction should be in such a way so that it causes a moment due to in the opposite direction, like this the moment should be. So how you will get this moment? By having a force which is acting upward. Okay.
Yes.
Yeah. And similarly here again, when you are looking this BC side, okay, here the moment is actually acting in this direction. Okay. So the net moment should be in a way like it actually cancels this. Okay. Like it should act in this direction. So you are putting the force towards the downward direction. Okay.
Yes.
Okay. So can you draw the axial loading diagram? For example, here the axial load will be here. It will be, say, for example, sorry. Here is a roller support. Okay. So will there be any horizontal reaction at point C?
No, sir.
Yeah. Yeah. For example, at point A, whether you will be having any horizontal reaction?
Yes.
Yeah. So RAH is equals to the magnitude of this will be P. Okay. So here we won't be having any horizontal reaction since this is a roller support. Okay. So when I'm drawing the axial loading diagram for the beam AC, okay, it will be looking like something like this. Up to point B, I will be having a compressive load. Okay. After that, the axial loading will be 0. Okay. It is like this, right?
Yes.
Okay. And for the shear force diagram, can anyone say how the shear force diagram will be looking like, whether it's positive or negative, or what will be the uh, structure of the shear force diagram?
So it will be positive up to B.
Okay.
No, sir, it will be throughout positive.
Yes,
Yes,
sir. Throughout.
yes, it will be positive throughout. Okay. Why positive? Because it is in clockwise direction. Okay.
Clockwise.
Yeah. So it will be p by 3. Here also p by 3. And can you say, can you draw the bending? I am drawing the bending moment diagram here. Okay. So what about the bending moment? This is A, this is B, and this is C. Okay. So what will be the bending moment at point B? For example, what will be the bending moment at point A? It will be 0, right? Since it is a hinged support, and also at point C it will be 0. So due to this value of Ra, I will be getting bending moment one value at point B, right? What will be the bending moment due to Ra at point B?
PL by 6.
Yeah, it will be PL by 6. And whether it will be positive or negative?
Positive.
Yes, positive. And at point B, I will be having one moment or two moments? Two moments, right? Because I'm having a concentrated moment also, which is acting at point B. Yes?
Yes.
So, and its direction is actually in the left anti-clockwise direction. So, it will be negative. So, I have to bring it towards the negative direction. Okay. So, this will be minus PL by 6. Okay. And then I can join it like this using a straight line. Whether this is clear or not, this is positive and this is negative. Okay. This is the same thing which we have learned earlier. Only thing is like here I have introduced some new thing called like magnitude of vertical reaction can be found by net moment on the beam divided by the total length of the beam. Okay. So can we proceed to the next problem?
Sir, on which
Sir, the net
condition it is
moment will be
usable?
Yeah, yeah. Go on.
sir.
Yes.
Actually, the net moment on the beam is only considering the concentrated moments, right?
Yes, yes. Only considering the concentrated moments. Okay.
In which condition it is usable? This condition net moment on beam upon.
And that's what, like this condition is used only when summation V equals to 0. Okay. And only when there are concentrated moments are acting on the beam. Okay, either concentrated moments or only moments, like it can be a uniformly distributed moment. At that time also you can use this condition. But there should not be any point load which is acting on the beam. Okay?
Sir,
Okay, sir.
Yeah.
sir on side BC,
Yes.
since we have a compressive in part AB, won't we
Yes.
have any reaction like tensile on part BC?
No, actually this part C is actually a roller support. So the part C is actually free to move.
Yes.
So we won't be having any compressive load in
So
part
actually,
AC.
if we had a fixed support, then we will have a
Yes, if we are having a fixed support, then you can't find RAH and RCH very easily. Then you have to go to the compatibility conditions and all. Like you have to find out the delta L of this beam equals to 0, and then you have to based on the compatibility condition you have to use. You have to find out the value of the horizontal reactions.
yes.
Yeah, got what I said, right?
Yes.
Okay. So now we will be moving towards shear force diagram and bending moment diagrams under distributed loads. Okay. So we will take a problem and then we based on that problem we can see the concept. Okay. So here is a beam like this. This is a hinged support and here another hinged support. Okay. And here I am having this is actually what
UDL.
Yes, this is uniformly distributed load. Okay, and then from part this to this, I will be having, and this is which type of load?
Triangular.
Uniform bearing load.
Yeah, uniformly varying load or triangular load. Okay. So this is point A, this is point B, and this is point C. Okay. So the uniformly distributed load is having 10 kilonewton per meter, and here the length of this is actually 20 kilonewton. 20 kilonewton per meter. Okay. So this is what type of beam actually, whether it's a cantilever beam or a fixed beam or a propped cantilever beam or something like that. Can you say which type of beam is this actually?
Propped cantilever.
Continuous beam.
Mm,
Overhanging.
Overhangs.
yeah, yes, it is an overhanging beam. Okay, propped cantilever beam is something like this. This is a propped cantilever beam. Okay, and propped cantilever beam is one type of statically indeterminate beams, which means like based on the static equilibrium conditions, we can't actually get the reactions supports. I mean reactions of the supports. Okay, and also this is known as continuous beam. Okay, this is continuous beam and this is propped cantilever beam. Okay, so now based on this diagram, first thing what we have to calculate, let's say this is 6 meter and this is 3 meter. Okay, now I have given all the data. Okay, so first what we have to calculate,
Reaction.
yeah, reactions. So how we will be calculating the reactions?
Summation vertical and moment.
Yes, summation vertical is equals to 0 and summation of moments is equals to 0. Okay, so when I write summation of vertical reactions is equals to 0, what it will give? So how I will calculate this? 10 kilonewton per meter I have given, right? So the total load of this rectangular or the uniformly distributed load will be equals to 10 into 6, which will be 60 kilonewtons. Okay. Yes.
Yes, sir.
Okay. So I'm taking the reactions like this. Okay. Let this be the direction of RA and this will be the direction of RB. Okay. So if I write net summation of, the summation of forces in the vertical direction is equals to 0, then RA, I'm taking all the upward forces as positive. Okay. So RA minus 60. And what will be the plus RB? Okay. Then what will be the, due to this uniformly varying load, what load will I be getting here?
30.
Yeah.
30.
Yeah, 30. Okay. So minus 30 equals to 0. So this will be one equation. And the next equation is like summation of moment equals to 0. So about which point can I take the moment to find either RA or RB? So I am taking moment about B. Okay. Okay, I am taking the moment at point B. What will be the moment at point B? Anyone?
So R into 6.
Yes. Actually, moment about point B, if I take, means it is actually equals to 0, right? Because there are no concentrated moments and this is a hinge support. So it will actually, there will be no reactions at this point B. Okay, so moment about point B is equals to 0, which means like RA. Okay, and here I am taking the sign convention as this is like normal sign convention for finding out the moment. This is similar to what you have learned in engineering mechanics. Okay, so here I am taking clockwise moments as positive and anti-clockwise moments as negative. Okay, so RA will produce a clockwise moment about B or anti-clockwise moment about B.
Clockwise.
Yeah, so I will be taking clockwise as negative and anti-clockwise as positive. Okay, so it will be minus RA into 6. Okay, then due to this uniformly distributed load, I will be getting a moment about B, right? And also due to this uniformly varying load, I will get a moment about B. So all these should be equated to 0. Okay, so based on this UDL, how we will actually take the UDL and how it will be acting is like, for example, the UDL force or the total force due to this uniformly distributed load will be acting at its centroid. Okay, you are getting what I'm saying, right?
Yes.
Yeah, for example, I can redraw this same figure. Let this be point A, this be point B, okay, and this be point C. So I can replace the same system by a system like this, which is 60 kilonewtons. And here this 30 kilonewtons also can be the total force due to this uniformly varying load is actually 30 kilonewtons. How we are actually getting that 30 kilonewtons? It is actually nothing but the area of this triangle, half into 20 into 3. Okay, so you will be getting 30 kilonewtons. Okay, so and it will be acting at which point? The centroid of the triangle will be at a distance of
1/3
yeah,
from
one third from the base,
height.
yeah, or the bigger side we can say. Okay, at
Yes.
one third about this here it will be acting. Okay, so it will be acting 1 mm, yes, I mean 1 meter from point B, which is 30 kilonewton, and this is RA. Okay, this is clear, right?
Yes, sir.
Okay, so minus RA into 6 plus due to 60 kilonewton, whether it is causing a clockwise moment or anti-clockwise moment with respect to point B.
Anti-clockwise.
Yeah, so I am taking it as positive. Okay, 60 into and the length is perpendicular distance.
3 meter.
Yeah, and due to 30, I will be getting a clockwise moment or anti-clockwise moment. 30 kilonewtons.
Clockwise.
Yeah, so it is negative. Okay, 30 into 1, which is equals to 0. So from here I will calculate the value of RA. Can you say what is the value of RA?
25.
Yes, 25 kilonewtons. So since it is positive, it is towards the upward direction. Okay, so from this I will be getting the value of RB also, which is like 90 minus 25, which is 65 kilonewtons, and it is also acting upwards. Okay, so now we have determined the support reactions. Okay, so the next point is like we will be finding out the shear force and the bending moment for this beam AB and BC. Okay, this whole ABC is a single beam, but we will be dividing it into sections AB and BC, and we will be finding out the shear force at any cross section between AB, and we will be finding out the bending moment at any cross section between AB and as well as between BC. Okay, so the next part we will be doing that. So for that again, what I'm planning is like I will be redrawing the figure. Okay, So this is point A and this is point B, this is point C. Okay, this is a uniformly varying load and this is a uniformly distributed load. Okay, and this is like 10 kilonewton per meter and this is the 20 kilonewton per meter. Okay, so here what is the reaction? 25 kilonewton, here is 65 kilonewton, right? And this is 6 meters and this is 3 meters. So what I will be finding out right now is like I will be finding out the shear force at any cross section between AB. Okay, so between AB, okay, or you can say AB also. Okay, from x is equals to 0 to x is equals to 6. So here I am taking this as x is equals to 0. Okay, this as the origin and this is x is equals to 6. Okay, so what will be the shear force that which is developed due to, or the shear force at any cross section? For example, let us take this, the cross section to be at a distance x from the left hand side. Okay, so what will be the shear force?
25 minus
20, yeah,
10x.
yeah, it will be 25 minus 10x. I will explain it. Okay, how we are getting. Okay, so actually how we got this 25 minus 10x is like, for example, in our earlier problems, like we have been seeing with respect to point loads, right? So with respect to point loads, we will be having only shear force which is a kind of rectangles. Okay, but whereas here the mostly we won't be having rectangles. Okay, so we have to find out, since this is a uniformly distributed load, then the procedure is like this. From we have to take a section from any of the left hand side or the right hand side. So since I have fixed this to be the origin, the left hand side to be the origin, then I am taking a cross section at a distance of x. Okay, so with respect to this cross section, we are actually finding out the what are the shear forces in the left hand side alone. Okay, so the shear force at the left hand side will be balanced by the shear force on the right hand side. Okay, so that is the logic. So we can take on any side what will be the shear force. So since in the right hand side we are having like mostly uniformly distributed load or the point loads, and as well as the uniformly varying load, whereas in the left hand side I'm having only single point load and a uniformly distributed load. So due to this, what happens is like the shear force I can find it out from the left hand side itself, which will be very much easy. Okay, since we are having only two loads. Okay, so based on this I'm actually taking the left hand side. Okay, so what will be the shear force due to this 25 kilonewtons? It will be positive or negative, because it is acting in the clockwise direction, right? When we are viewing it from the left hand side.
Positive.
Yeah, so it is positive. So only I have written it as positive 25. Okay. Now coming to the uniformly distributed load. We have already said like the uniformly distributed load per unit length, which is equals to 10 kilonewton per meter. Okay. So here I have taken it the distance as x meters. So the total load will be how much? 10 into x. Okay, and the loading direction is actually downwards, so it will cause a anti-clockwise movement. Okay, so due to this the shear force is here we have given it as negative value. Understood? Is it clear to everyone how we are actually calculated the shear force at any cross section xx? Or should I have to repeat it? Understood, right? Okay, anyway, I will repeat it further. Okay, see, first we are actually taking a cross section between AB. Okay, now what we are actually doing is like we are splitting the entire beam into two parts. One is between AB and another one between B and C. Okay, for AB we will be having a separate shear force and bending moment equation, whereas for the part BC I will be having a separate bending moment and shear force equation. Okay, so after having selected this part AB, I am taking a cross section at a distance of x from the origin. Okay, so now in order to calculate the shear force equation, whether I can either take both, I can either take on the left hand side or I can take the loadings on the right hand side. But since in the right hand side I am having a uniformly distributed load and a point load as well as a uniformly varying load, it becomes very difficult. Okay, so whereas in the left hand side I'm having only a point load as well as a uniformly distributed load. Okay, so due to this I'm taking the loadings based on the left hand side. Okay, so here due to point load I will the shear force or these based on the sign convention which we are following, so the shear force of 25 kilonewton is actually positive, so only I have written it as a positive value. Okay, and due to this uniformly distributed load which is actually 10 kilonewtons per meter. Okay, so due to this, I should calculate the total load on the left hand side. The total load on the left hand side will be 10 kilonewtons multiplied by x meters. Okay, so it will be 10 into x, and the sign of for 10 into x will be based on the sign convention which we are following. Here in this case, it is actually in the downward direction and it is causing a anti-clockwise direction. So it is like minus 10x. Okay.
Yes.
Yeah.
Yes.
Okay. So now let's proceed to the bending moment equation. So bending moment at section XX. How I will calculate the bending moment at section XX? Okay. Here also again we are actually taking the loadings with respect to the left hand side alone, not with respect to the right hand side. Okay. Since in the left hand side we are having very less loads. Okay. So due to this 25 kilonewton shear force, what bending moment I will be getting at cross section XX?
25 into x
Yeah,
positive.
positive. Good. 25 into x. Yeah. And then due to this uniformly distributed load 10x, okay, how much of then what is the procedure for this uniformly distributed load is like I have to take the total load of this entire section up to this x. Okay, and what will be the total load? We have actually seen it is 10x, right? Okay, it is 10x, and for calculating the bending moment it should act at the centroid of this area. Okay, centroid of this area. What is the centroid of this area?
X by 2.
Yes, it is x by 2. So if I redraw this again, okay, this entire section we are actually converting it to like a point load which is acting of total load 10x, which is acting at a distance of x by 2. Is it clear or not?
Yes, sir.
Yes. So the total load 10x into x by 2, and whether it's positive or negative.
Negative.
Yes, since it is left anti-clockwise, right? So it will be 10 into x by 2, which will be x square by 2. Now we have got the shear force and the bending moment equation for the part AB. So if we are, for example, in the question, if they are asking what is the shear force at point, say, 1.5 meter from point A, okay, 1.5 meter from point A, then you can substitute in x equals to 1.5 and then you can calculate the shear force and the bending moment at x is equals to 1.5. Okay.
Yeah.
Okay. So between part AB is over. Okay. So coming to part BC. Okay. 1 minute. I will switch on the Laptop power. Okay. Yeah. So between point BC. So which part can I take here as the origin? Any idea whether can I take origin as at B or whether can I take origin at C?
C.
C. Yes. Why we are actually taking origin at C? Any idea why we are taking origin at C?
Sir, then reaction not come into picture.
Reaction anyway, it is going to come into picture. Okay. Okay. Even though, see, for example, even if I take x is equals to 0, then also reaction won't be coming into picture at point B. See, for example, if I am taking the origin at point C, okay, this is B, this is C. Okay, for example, if I am finding out the, for example, if I have taken the origin at point C, then I will take a cross section which is x distance from here. Okay, this is the cross section. So here what I'm having is like a triangular area. Okay, so it is easy to find the area of a triangle and the centroid of a triangle. Whereas here, if I have done like this, okay, x is equals to 0 and x is equals to 3, and this is point B, this is point C, and if I have taken a cross section like this, okay, which is at a distance of x, then what should I have to calculate? The area of this trapezium I have to calculate, right?
Yes, sir.
So only we are actually taking the origin from at point C, okay, so that we can calculate the area of the triangle easily, and then we can calculate the centroid of the triangle easily. Whereas here I have to calculate the area of the trapezium, and then I have to find out the centroid of the trapezium, so which will be somewhat difficult when compared to the right hand side. Okay.
Yes, sir.
Okay, so this is the section XX, and then can you say what will be the shear force at section XX? First of all, what will be the length of this load at section XX? Anyone?
20x by 3.
Yes, it will be 20x by 3. So why it is 20x by 3 means, for example, this is the whole loading diagram of this uniformly varying load, and this is 20, and this is the length which you want to know. Okay, and this is x, and this is total length is 3. Okay, so based on similar triangles, if you are going 20 divided by 3, which is equals to wxx, that is the loading at this section. Okay, which is wxx divided by x. So wxx will be 20 into x by 3. Okay, so based on this, can you say what will be the shear force? Now I know this is 20 into x by 3. Okay, so what will be the shear force at shear force for this section XX?
Half
And- Yeah, half into?
x into 20x by 3.
Yes, half into x into 20 into x by 3, which will be 10x square by 3. And whether it's positive or negative?
Positive.
Yes, it is positive, since like we are analyzing the right hand side, right? So we have already told, like, based on any cross section, if the shear force is like this, then it is a positive. Okay, so we are actually analyzing only the right hand side, so shear force will be positive. Okay, now coming to the bending moment value. Bending moment at the section XX.
Sir, please repeat this point. Sign convention from right hand side.
Okay, I will repeat it. See, for example, for shear force, what sign convention we are actually doing is like, for example, let this be the cross section XX. Okay, so if the left hand side net force is actually upwards means then it is positive. Okay, and in the right hand side if it is downwards means then also it is positive. So this is the sign convention which we are actually using. So here, since we are analyzing only the right hand side, and then in the right hand side we could see all the loadings, it is in the downward direction, so it is positive.
Okay, sir.
Okay, yeah. And then what will be the bending moment? Again, which side I will analyze? Again, I am analyzing the right side because right side is easier to analyze since this is a triangular section. Okay, so again I will take this piece of triangle. Okay, this is actually what, 20x by 3, right? And this is at a distance of x. So what will be the what should I do now for calculating the bending moment? First I have to find the total area of this triangle, and then I have to locate the total load at the centroid of this triangle. Okay, that is the procedure. Okay, so what will be the total load of this triangle? It will be 10x squared by 3, right?
Yes.
Yeah, and it will be acting at a distance of
X by 3.
yeah, x by 3 from this side. Okay, so if I'm replacing this by an equivalent loading, okay, here I'm replacing. Okay, so it will be 10x squared by 3 at a distance of x by 3. Okay, so what should I do here now? It should be 10x squared by 3 into x by 3, right? So whether here the bending moment is positive or negative?
Negative.
Yes, since it is right clockwise. Okay, so up to this it is clear, right? So for any kind of bending moment diagram or the shear force diagram, you can do like this. For example, this equations will be very much useful when they are asking the, for example, what is the shear force at say at x is equals to 4.5 mm from the from point A or something like that. When those kinds of questions are asked in the exam, then at those times these equations will be very much helpful. Okay.
Sir, here we are seeing bending movement from right hand side. So
Yes.
it will not be positive.
No, yeah. See, for example, you are seeing the bending moment from the right hand side, right? And right hand side, what is this is the total load, right? 10x square by 3,
Yes, sir.
and it is creating a moment like this, right? So it is like right clockwise direction.
Yes.
So what we have followed is like left clockwise and right anti-clockwise are positive. So here it is 10x square by 3 is causing a moment in the clockwise direction. Okay, with respect to this cross section XX. So only we are putting a negative sign. Clear or
In
should
case
I?
of
Yeah.
in case of left hand side,
Hmm.
the both SFD and BMD clockwise gives positive.
Yeah, in case of left hand side, for example, for shear force it should be upward direction. Okay, and for bending moment also it should cause a bending moment in the clockwise direction for the left
Clockwise.
hand side. Yeah, whereas for the right hand side it should be in anti-clockwise direction. For example, it should be like this when I'm taking the section XX. If it is like this means then it is a positive bending moment. Okay.
Means from right hand side, both shear force and bending moment should give anti-clockwise.
No. Actually, don't confuse between both shear force and bending moment. For shear force, you have sign convention like this, right? What I have told you here. This is the sign convention for shear force diagram. Okay.
Yes, sir.
Yeah. For bending moment alone, what I'm saying is like in the left hand side, it should be causing a clockwise moment, whereas in the right hand side, it should cause an anti-clockwise moment for bending moment alone. So based on this shear force, see this shear force is acting downwards and it is causing an anti-clockwise, I mean clockwise moment, right? With respect to this cross section XX.
Yes.
So only I'm writing this as a negative value. Okay, see here I am isolating this right hand side alone, this triangular area alone, and then I have converted this triangular area into a point load of magnitude 10x squared by 3 acting at a distance of x by 3 from the cross section. Okay, and when I actually find out the moment due to this 10x squared by 3 about this cross section, then it is causing an clockwise moment in the right hand
Yes.
side. Yeah, so only I have written it as a negative value.
Sir, from the right, if it is anti-clockwise, then it is positive.
Yes, right, it is anti-clockwise means it is positive for bending moment.
Yeah.
Okay.
Usually, if we consider the entire beam, then only we consider this TBL, what you do.
Yeah, if if you are considering it as an entire beam and you are having some concentrated moments like this, then only you will be considering it as a TBL condition. Since here
Okay.
uniformly distributed load, point loads, everything is there, then you have to go by this procedure: left clockwise, right anti-clockwise. Okay. Sorry. Clear? Maybe we will be doing more problems on this, then it will be very much clear. Okay. So now we have calculated the bending moment at for section AB and as well as bending moment for section BC. Okay. So from here you can actually calculate what is the shear force at point A, what is the shear force at point C, and what is the shear force at point B, and what is the bending moment at point B. Okay. Can you do that? And can you say what is the shear force at point A and what is the bending moment at point A?
Sir, in section BC,
Yes.
for shear force, should we consider the reaction from B?
No, we won't be considering the reaction from D, since like
Okay, if we say the left side, it will be
yes.
considered.
So we are only looking at from one side, right? Either you have to look from the left or you have to look from the right.
Got it.
Yeah. So can you say what will be the shear force at point A?
25.
Yes. So how you are getting 25? Like substituting at x is equals to 0, you will get 25. Okay. And what will be the bending moment at point A?
0.
Yeah, 0. And for shear force at point C?
Zero.
Yes, it is 0. And bending moment at point Z will also be 0. Now coming to what is the shear force at point B? Anyone? What is the shear force at point B?
30.
30.
Yeah, someone was saying 30 and someone was saying a different answer, right? So here what we will be doing is like when B is considered as part of the part BC or part AB, we will be getting shear force, right? Which is equals to, for example, in this for x, I will put x is equals to 6. Okay. And at that time, what shear force I am getting?
30.
Minus 30.
Yeah, minus 35. And then when I'm considering the point B as part of part BC, then what shear force I'm getting at point B?
30.
Yeah. 30 or yeah, it's 30. Okay. And what is the value of the bending moment? Similarly, if we are calculating what is the value of bending moment as part of part AB and as part of part BC? Anyone?
Minus 30.
Yes, it is minus 30 kilonewton meter. Okay. So what is this actually? Whether can you represent this all this data, okay, by a shear force and bending moment diagram? Okay. Now the next step is that now we will be representing all these values as a shear force and bending moment diagram. Okay. For example, this is ABC.
Sir, that means reaction at B is not taken account.
No, reaction is actually taken into account. Okay. See, for example, the reaction is 65 kilonewtons at point B, right? So only you are getting this variation minus 35 to 30, and this variation is caused due to this concentrated load or the reaction load.
Okay.
Okay.
Sir,
Yeah.
bending moment in both equations, we are getting minus 30 kilonewton.
Yes, bending moment you will be getting minus 30. Why? Because you are not having any concentrated moments here. If you are having some concentrated moment at point B, then you will be having some different values. Okay.
Okay, sir.
Yeah. So can you draw the shear force diagram and can you say how it looks like? First I will draw the loading diagram and then I will go for shear force diagram. Okay. So this is a uniformly distributed load, right, up to point B. And then from point B to C, it's a uniformly varying load. Okay. So can anyone say what is the variation of the shear force? I mean, we have calculated, right?
Linear.
Yeah, it will be linear. For example, at point A, what is the shear force value which we got? 25 kilonewton positive. So what I will do is like I will mark 25 kilonewton here. Okay, this is 25 kilonewton. Then at point B, I am having two different values of shear force. Okay, one is minus 35 and another one is plus 30. Okay, this I will name it as minus 35 and this I will name it as plus 30. Okay, and shear force at point C is actually 0. So for example, here what will be the variation? Since you are having a uniformly distributed load, okay, you will be having the variation like this. Okay, and then again from here to here, before going to this variation, I will say one topic, I mean say one concept and then I will go to this variation. Okay, for example, the concept here is like the loading actually, for example, Wxx, if you are taking as the loading at any point, okay, which we can say here as 10 into x, like that. Okay, here the load at any cross section, here we can say it as 10 kilonewton per meter. Okay, and here we can say it as 20x by L, like that only we have studied right earlier. Here we have analyzed, right, 20x by L, and then here 10 kilonewtons per meter. So the slope of the shear force diagram which will be equal to the load intensity. Okay, the slope of the shear force diagram at any cross section will be equal to the load intensity. This is one concept, and the second concept is like the slope of the bending moment diagram will be equal to the shear force. These two are very, very important concepts. Okay, based on this only, without even going to the equation, we will just draw the bending moment diagrams for all the loadings. Okay, these two are very important. Okay, so from this, what can you say about here? For example, here Wxx is actually constant, right? For uniformly distributed load, Wxx is constant. Correct or not?
Sir, it is 10x, na?
No, 10x will actually be the total load at any cross. For example, if you are taking a cross section like this, then this is 10 and this is x. Then it will become total 10 into x as the area of this whole figure or the shaded region. Okay, but here 10 is actually constant, which is like here everywhere you will be having 10 kilonewton per meter as the variation of the distributed load. That is termed as uniformly distributed load, right?
Yes, sir.
Yeah. So here Wxx is constant. So what will be the slope of shear force diagram? It will be constant. So only we are actually going through a linear line. Okay. Whether this part is clear or not. Since here Wxx is constant from part A to part B, you are actually this by this concept slope of shear force diagram is equals to the load intensity. So due to that, we are actually having the slope of the shear force equal to constant between part AB. Okay, this slope is actually constant. Okay, then coming to this triangular part. Okay, so triangular part, whether what will be the slope of shear force?
Reducing.
Yeah, it will be reducing since the loading is actually reducing. So you are having 20x by 3, right, as the loading part. So it when you are actually integrating this, for example, 20x by 3 is the Wxx part, which will be equals to dfxx divided by dx. So if you actually want to calculate the dfx, it will be like a reducing curve, or it will be a parabola. Okay, parabola of second order. And this, either I can draw like this one parabola, or I can draw a parabola like this. What is the difference between these two parabolas?
Slope is increasing for one and slope is decreasing for another one.
Yes. For this, let's say this is 1 and this is 2. Okay. So for which case slope is increasing and for which case slope is decreasing?
For one, it is decreasing, and two,
One increasing and
one
Yeah,
increasing. Yeah.
for 1 it is increasing. df by dx is actually increasing for 1, whereas for 2 df by dx is actually decreasing. Okay, so here the load intensity actually reduces, right? So the shear force diagram should also, the slope of shear force diagram should also reduce. Okay, so which diagram suits here, 2 or 1?
2.
Yeah, 2. So from B to C, the slope of, the load intensity reduces. So due to that, from B to C, the slope of the shear force should get reduced. Okay, so 1 is wrong. So up to this, it is clear or not?
It's clear.
Yeah. Okay.
So can you kindly repeat the last part?
Okay. See, for example, from A to B, it's clear, right? How we are having a constant slope for the shear force diagram.
Yes, sir. Since it is constant there, it will
Yeah.
be linear.
Yeah, since the load intensity is constant here, it will be linear for the shear force diagram. Whereas for the B to C, the loading is actually decreasing from B to C. Okay, therefore the slope of shear force diagram also should decrease. For a straight line or the linear line, you will be having constant slope only. So the next thing is like parabola. Okay, so for parabola, you can draw two types of parabola. One is like a decreasing slope parabola, and another one is like an increasing slope parabola. Okay, so since the load intensity actually decreases from B to C, so I have to draw the decreasing slope parabola from B to C. Now it's clear.
Yes. Yes, sir. Since the slope is decreasing, we are drawing this type of parabola.
Yes. Why the slope is actually decreasing we are choosing means because the load intensity decreases from B to C.
Yes.
Yeah, since the load intensity decreases from B to C, we need a parabola which is having a decreasing slope. So only we are drawing a parabola with a decreasing slope. Okay? Yeah. So then I will take this as point D. Okay? So can you find out the point D? At from which position from point A is point D located where shear force is actually 0? This is 25 and this is 35. So can anyone find out what is the position of point D? Or any method to find out what is the position of point D?
So from the equation first of AB, we can
Yeah.
put shear force is equal to 0.
Yes, that is one method. Yeah, that is also correct. And then you can also from using this similar triangles also you can find out. So can anyone say what is the position of point X from A or point D from A?
2.5 meters.
Yes, it is 2.5 meters. For example, here I am doing by similar triangle method, and the other method is based on shear force equation. Okay, so I'm assuming this as X, and what will be the distance of this when I'm considering point B alone? It will be X minus 6, right? Or 6 minus 6. Okay, 25 divided by X is equals to 35 divided by 6 minus x. From this, x is equals to 2.5 meters. Okay, and this is the shear force diagram. Now can we come to the bending moment diagram? So since we are having extra point D, can anyone say what will be the bending moment at point D and how you will find out the bending moment at point D?
Putting 2.5 in the equation.
Yes. So what you are getting by putting 2.5 in the equation for AB, bending moment? What is the bending moment at point D?
31.25.
Yes, 31.25 kilonewton meters. Okay. So then here what will be the variation from A to D? For example, here I have to write A, then corresponding to this D point I have to write D, then corresponding to B I have to write B, and then here C. Okay. So now can you draw what will be the bending moment variation from A to D? Here we have said, right, the slope of the bending moment equal to the shear force, right? So here the shear force is actually decreasing linearly. Okay, correct or not? From A to D, the shear force is actually decreasing linearly. So from A to D, the what will be the shape of this A to D? Whether it will be a parabola or linear or like a constant rectangle?
Parabola.
Yeah, it should be a parabola because it is one order higher. Okay. So, and what will be the shape of this parabola? Whether I should draw with an increasing slope or decreasing slope?
Decreasing.
Yes, it should be a decreasing slope. So this is the case of decreasing slope. If I draw the parabola like this, means then it's the case of increasing slope. Okay. So now you are getting how we are actually drawing the parabola between A and D.
So actually, in previous SFD,
Yes.
the parabola which we drew was like which you drew for right node, sir. Like, increasing one which you drew. It's a
No.
bit confusing. The shape of the curve.
Okay. See, actually, the parabola is actually dependent based on from which point you are going to which point. Okay. For example, from B to C, I have to come, right? So only two options I have. For example, here I have point B. Okay. And here I have point C. From here to here, I have to connect using a parabola with a decreasing slope. Okay. So only one option I have, either this or this. Okay. So this is a parabola with increasing slope because you can see the slopes are increasing as it goes. Whereas here the slope is decreasing. So this parabola I have chosen for BC. Whereas here I have to connect it from, see, this is actually what 31.25, right? And it is positive also. So I have to connect between A and D from here to here using a parabola. Okay. So either I should draw like this, a curve should be drawn like this, or a curve should be drawn like this. You are getting right? So this is 1. Yeah, this is 2. So here if you are seeing 2 is actually having an increasing slope. You can actually see with respect to x, y actually increases very fast. Okay. Whereas 1 is having a decreasing slope. Okay. Here,
Yes, sir.
yeah. So based on this only, I have drawn one like this.
And when will we have the SFD like that one?
SFD, when you are like this, right? You are asking question like this. See, for example,
Other ones.
Yeah, other one. Based on this uniformly varying load. For example, if I have triangle like this, from B to C, if I had triangular loading like this or uniformly varying loading like this, then here shear force actually increases from point B to point C. Then I should have a parabola with an increasing slope. Then I will go for this. Let's say 1. Okay? Or should
Yes.
I have to repeat it?
Clear.
Yeah. Getting it right, what is the concept, everything. So this is very important for gate. Okay. Now we have drawn the parabola from A to D, which is 31.25 kilonewtons. Okay. This is bending moment at point D. Then from point D to B, what is the variation? For example, what is the bending moment which you got at point B from the calculation which you have done?
Minus 30.
Yes, minus 30. So this is minus 30. So from here to here, you have to come by some parabola. Okay. Because here the variation is actually, the shear force is actually varying. So here it should be a parabola. So what will be the slope of that parabola? Whether it should be increasing or decreasing. Here you can see, right, the shear force from D to B, whether it is increasing or decreasing, regardless of the sign.
We should take the absolute value. is it?
Yes, absolute value.
Increasing.
Yes, it is increasing. So the slope of the bending moment should also be increasing. So whether I should draw a parabola like for example, a parabola like this. Sorry about my drawing. Okay. Or whether I should draw a parabola like this. Yeah. Which one? Like, let's name this as number 1 and this as number 2. Which is correct? Number 1 is correct or number 2? First, what is the situation we want? Like, the slope should be whether increasing or decreasing.
Increasing.
Yeah, it should be
Increasing.
increasing. So which one suits here?
2.
Second
2.
one.
Yeah, second one. So we will erase the first one.
Sir, how to
Yeah, how to? Yes,
how to check slope?
how to?
Check slope, sir, slope.
Okay, see, for example, maybe I will draw in a separate slide. Here I will draw. This is a parabola, okay? Imagine this is a parabola, okay? Here you can check the slope like this, okay? For example, for a particular value of x, okay, here x should be constant, okay? Here I have taken the x value as very high. For example, take equal intervals of x. For example, let this be the length of del x, okay? So if I calculate the length of del x here, the slope will be delta y divided by delta x. Here the slope is actually small, okay, because slope is delta y by delta x. Here delta y is actually very small when compared to delta x, okay. But as you go on keeping the delta x as constant, as you go on through the parabola from this point to this point, okay, for example, let this be a and b. From a to b, if we are proceeding, okay, the slope actually increases, right? Because delta y is
Yes, sir.
increasing with respect to
Yes.
the curve. So this is termed as a increasing slope. Slope is increasing. Okay.
Sir, we should always see magnitude of news
No, no.
for SFD as well as BMD.
Yes, for SFD as well as BMD, you should see only the magnitude to get the slope, whether it is increasing slope or decreasing slope. For example, here, since even though shear force is negative, but shear force is increasing in the negative direction, so the slope of the bending moment should be also be increasing. Okay.
Yeah. Yes, sir.
Yeah. So now coming to this next second parabola. Okay. So here from point, let this be point A and this be point B. So if you take here, this is the delta x and this is the delta y. Okay. Here delta y is way greater than delta x. For example, here if I take another one point and if I see here delta y actually gets reduced, right? When we are going from point A to point B.
Yes, sir.
Yeah.
Understood.
Understood?
Yes, sir.
Yes. So based on this thing only, we are actually calculating whether the slope is decreasing slope or increasing slope, and how we are going to draw the shear force diagram and the bending moment diagram. Okay.
Yes.
Yeah. So up to point B, we have done the drawing of bending moment. So from point B to point C, how we should draw whether the shear force is increasing or decreasing from point B to point C.
Decreasing.
Yeah, it is decreasing. So the shape of or the slope of the bending moment diagram should also decrease, right? And for example, if this is in the order of x square, okay, x square is also parabola, right? And x cube is also a parabola. We will term this as cubic parabola, right? So if this is a variation in x square, this will be a variation in x cube. Okay. So here, yeah, which the slope should be decreasing. Okay. So I'm drawing a parabola like this. And its slope is decreasing. Okay, it's clear or not? It's clear, right?
Yes.
Yeah. So shall we proceed to the next step? Okay. So this is a cubic parabola, and you can see from the equation also, like for example, from B to C, what is the variation of this bending moment? It is in x cube only, right? 10 x cube divided by 9. So from this also you can see it is having a cubic variation. Okay. And whether can you, for example, when the bending moment changes sign, at, at the point at which the bending moment changes sign, what you will term that point as?
Point
Well,
of contraflexion.
yeah, it is called as the point of contraflexion. Let's name this point as E. So how can you find this point of contraflexion? At which distance it is located like that?
Shear force is maximum at that point.
Okay, but see, you
Or
can.
it's equating zero.
Yes, it is actually equating bending moment equation to 0. Okay, bending, and since this is located in which part, AB part or BC part? AB part, right? So you have the bending moment equation in the AB part, which is 25x minus 10x square. When you are equating this to 0, then you will get the value of x. Okay, and that will be the point of contraflexion.
Sir, is it also known as point of inflection?
Yes, I think both point of contraflexion and point of inflection are same. I'm not very sure about that.
So which means the slope of the shear force diagram will be 0.
Yes, for example, when bending moment is actually 0, then what we can say about the shear force is it is actually maximum. Correct or not?
Yes. Yes.
Yeah, when shear force is actually maximum, then bending moment is actually 0. But mostly you go by this rule. When bending moment changes sign, then that point is called as the point of contraflexion. Because why I'm saying this is like, for example, you will be having concentrated moments or concentrated shear force like that and all. So at that time, these concepts like maximum shear force and all those won't work. Okay. Understood?
Yes, sir.
Yeah. So based on another concept also here I wish to give here. Okay. For
Sir,
example,
and
yeah.
so as per above SFD, if we try to locate E, then it seems that it is not maximum. It's a shear force.
Sorry, your voice is actually breaking. So, hello. Yeah. Yes.
So in our diagram,
Hmm.
at point E on ESFD, if we try to plot, then it is not corresponding to maximum shear force because there are mixture of loadings.
Yes, they are having concentrated shear force loadings. So it won't coincide with when shear force is maximum, like bending moment is 0. That won't occur.
Okay.
Yeah. Okay, so from here what we can actually infer is like I can actually integrate these two equations also. Okay, let this be number 1 and this be number 2. Okay, for example, fb minus fa equals to integration of a to b wxx dx. Okay, like this also I can calculate what is the value of b and what is the value knowing when I know the shear force value at a. Okay, for example, can you apply this here? For example, I need fb. Okay, and here the only thing is like you have to take care of this sign convention of wxx around. For example, if the load intensity is towards downward direction, then Wxx should be negative. Okay, and if the load intensity is towards the upward direction, then Wxx must be positive. Okay, so Fb minus Fa, what is the value of Fa, shear force at point A? It is 25, right? Yes or not?
Yes, sir.
Yeah. So, and what is the value of Wxx? It is minus 10. Integrating it from 0 to 6 into dx. Okay. And what is the integration of this? Minus 10 into x. Applying the limits from 0 to 6, which will turn out to be minus 60. So, Fb minus 25, which is equals to minus 60. So, Fb equals to minus
35.
Yeah, minus 35 kilonewtons. Okay, from this concept also you can calculate the value of Fb without even going to the equations or without even drawing the shear force diagram. Directly you can calculate. This method will be helpful when they are asking what is the shear force at point B, what is the shear force at point C, like that. Okay.
This method only work for UDL and UVL.
Yes, this method works only for UDL and UVL. Only then you can actually get the Wxx variation, right? For point loads and all, the shear force variation is actually constant. So directly you can actually tell the answer from for point loading conditions. There you don't have to go for this integration and all. Okay. But at point
Sir,
B,
have you considered this minus?
are we considering
The minus in the formula?
Yes.
We had minus
Here,
Wx.
here minus y we are actually using is like load intensity in the downward direction is taken as negative. Here you could see Wxx, the load intensity is in the downward direction. So we are
for
taking,
this case only we are taking this sign convention. Huh?
yes, for only this you are taking this sign convention.
So in that formula also it has the same meaning, sir.
Here
Minus
also,
Wxx equal.
yes. Here also it has the same meaning, but since you are here, you are very much looking only at the slope. Then you are actually drawing like a linear line. Okay. Here you are not going for see, for example, here you are taking the load intensity, it actually reduces or decreases. So you are actually calculating the slope value as decreasing slope. Here you are not calculating whether it is in the downward direction or upward direction or something like that. Okay. But when you are using this formula, integration formula, at that time, then you have to use the sign convention, like downward is negative and upward as positive. Okay, only if you practice these problems, then only it will be very much clear. Okay, I will give you some homework problems and I will upload all the homework problems by tomorrow, within tomorrow night. Okay.
On G Drive, sir, right, sir?
What?
Actually, will you upload those problems on Google Drive?
Yeah, Google Drive. Yeah, Google Drive. Yes. Okay, up to this it is clear. So at point B itself, we are having two shear forces, right? So this we have taken only for section BA. Like similarly, we can do it for section BC also. Okay. For example, FC minus FB equals to integration of, or else like C from B to C Wxx dx. Okay, which in the case here, in this case FC equals to 0. Okay, I'm always using upper minus lower limit. Okay, upper minus lower is equals to lower limit to upper limit Wxx dx, which is equals to 0 minus FB equals to integration of 0 to 3. What will be the value of Wxx? It will be 20x by 3, right? And it should be negative value. So negative sign, I'm taking it here. Dx. So minus FB equals to 20 into minus 20 into x square divided by 6. And if you are applying the limit, what value are you getting here? 20 into 3, when I am applying, it will be like 9 divided by 6. So it will be
30.
3, yeah, 2. Yeah, it will be 30. And you are getting a positive value. And that is the thing which we are getting in this diagram. Okay. So while you are using this, you have to make sure from which is the upper limit and which is the lower limit. For example, here I am always taking b minus a. Okay, this I am setting as the upper limit, b minus a, which is equals to the integration of wxx dx from a to b. Understood, right?
Yes, sir. Actually,
Yeah.
if we have any point load or concentrated moment in between the points which we consider, then we can't use this. No?
Yes, then you can't use this. But still, if you are not see, if you are for example here and all, like for example here at point B, say if you are having a concentrated moment, okay, at the time here the moment, I mean you can't use this formula, but whereas up to this section you can use the formula. Okay, up to D you can use, whereas at
So at
point
the end point, and if we consider the upper limit and lower limit, if we have at the limit, then what will happen? At the end point, if we
yeah,
have
at the
any
end point if you have some concentrated moments, then you can't use this method. Okay, then you have to,
concentrated loads.
yeah, concentrated loads you can't use. Concentrated
Okay.
moments I'm saying. Okay.
Okay.
Yeah. Based on the loading diagram alone, we have calculated. Here you haven't taken. For example, this based on this 10x, you haven't taken what is the reaction of these things, supports, those things and all you haven't taken, right? Only based on the given loading conditions, you have found out what is the shear force at A, what is the shear force at B. Okay.
By
So
this method, can we find
yeah,
load from T?
can you repeat one more? Your voice is actually breaking.
Hello, sir.
Yes.
Hello. By this method, can we locate the position of point D?
Yes, that also. No. Point D you can't actually locate through this method. But one thing you
Okay, sir.
can do, what you can do is like you can actually find the moment at point D using this method. Okay, since you know what is the value of x. Okay, for example, if I am writing MD minus MA, okay, that is the second thing, second concept. For example, we have already written dm by dx is equals to uh, shear force, right? Shear force at any section f of x. Okay, so if I want m, okay, which is equals to df, I mean f into dx, okay, f of xx into dx, integrating it from a to d. So in the left hand side, what I will get, md minus ma equals to integration of a to b f xx dx. And what ffx dx means what? It is the area of this triangle, right? Area of this triangle, this portion, right?
Yes.
Yeah. So what I should do? MD minus MA. Here you have to take the sign convention. Okay. Like for example, if it is above, then you have to take the shear force as positive. If it is below, then you have to take the shear force as negative. So since here it is in the above, then shear force is positive. So you can write it as what is the area of this? Half into 2.5 into 25, right? Half into 2.5 into 25, and the sign you have to give here as positive, and this will turn out to be 31 point,
31.2.
yeah, 31.25, and ma is actually 0, so md is equals to 31.25. Okay, like this you can also calculate like from point B to D. For example, MB minus MD I can put, and I can find out the area of this. And here I should use negative value. Okay, that also we can do. For example, MB minus MD equals to minus, since the shear force is in the negative direction, negative. Okay, and what will be the area of this? 1 by 2 into 35 into 2.5, which means 3.5, right? 1 by 2 into 35 into 3.5, and from this you can calculate MB value. Okay, can anyone say what is the MB value, whether it is matching with the earlier one? Anyone? Okay, so you check the value of MB and then you see whether it is giving the correct answer or not. Okay,
30
30, it is giving correct answer, right?
minus 30.
Yeah, thank you. Okay then, so this is the overall concept, which is with respect to the bending moment diagram as well as the shear force diagram. So from now onwards, we will work out some more problems so that it will be very much clear. Okay, so let's go to the new problem. Okay, again, as within today night, I will be uploading the video in the Google Drive. Okay, if we have any doubts, like again you revisit the same problem which we have done. Okay, and work out the same problem, and then you see if you have any doubts, and then we can clarify all your doubts in the next class. Okay, so we will wind up this last problem.
Okay, sir.
Yeah, so here this is a cantilever. Yeah.
Actually, if this kind of problems if we have to face on grid, then how to solve this in a shortcut way?
See, the shortcut is based on the type of question which they are asking. Okay, for example, if they are asking what is the for example, let's say, suppose they have given a problem like this. Okay, this is actually a uniformly distributed load. Okay, they have given a problem like this, and they are giving 4 options. Okay, in the GATE exam they are giving 4 options, like what is the shape of the shear, or please select the correct shape of shear force diagram, like that they can ask. Okay, at that time you don't have to find out the shear force equations, bending moment equations, like that. Directly you can use the concept of this slope concept. Okay, like increasing slope, decreasing slope, based on this uniformly distributed load, like that you can directly apply that concept. But if they are asking what is the bending moment at point B, or what is the bending moment at point A, then you see to that whether you can first draw the shear force diagram, and then whether the shear force diagram is actually easy, or like what can we say, whether the shear force is having only triangle or rectangles. Then you can easily calculate what is the bending moment at point B or point A, something like that. Okay, if all of these things is not clear, and if they are asking like what is the bending moment at say in between point A, or what is the maximum bending moment, then you have to go for equations. Okay, maybe if we are solving more problems, then it will be clear. Okay, maybe after this problem I will say everything clearly. Okay, yeah.
Okay.
Yeah.
Thank you, sir.
Fine. So for this problem AB, and it is of length L. Okay, and this is of W kilonewton per meter, which means it is, what type of loading this is this?
UDL.
Yeah, UDL. So, and it has W as the kilonewton per meter. Okay, so, and this is a cantilever beam. Okay, so first the step is to find out the reactions. Okay, so I will proceed very fast. Okay, what is the reaction here? You will be yeah, W into L, which means like the W per unit length into total length, which is L. So you will be having the total load as W into L. So that you will be having as the reaction at point A. And whether you will be having a moment reaction also, right?
Yes.
And yeah, and how you will calculate the moment reaction?
WL into L by 2.
Yes. So WL is the total load and it is acting at a centroid or the central position. Okay, which is L by 2. So WL is the total load into L by 2 and it will be acting in this direction. So the moment reaction should be opposite to that, right?
Anticlockwise.
Yes, anticlockwise. So WL square by 2. Okay, which is MA. So with this concept alone, whether can you draw the shear force diagram and bending moment diagram without going to the equations? For example, let this be shear force diagram. Okay, let this be point A and point B. Okay, what is the shear force at point A?
WL.
Yeah, it is positive or negative?
Positive.
Yes, so WL have drawn it like this. Okay, and what will be the variation from A to B? Whether it is a constant like this
Linear.
or yeah, it will be linear. And what will be the shear force at point B?
0.
Yes, it will be 0. So you have to collect this with linear. And what will be the whether it will be, why I have drawn a parabola here? Why I am drawing a linear here? Why I haven't drawn a parabola? And this is a positive value. Okay. The concept which we have studied is like the slope of the shear force diagram is equals to the load intensity. Okay, here the load intensity is constant through the length. Okay, therefore the slope of the shear force diagram between A and B must be constant. Okay, so only I have drawn a linear curve here. Is it clear or not?
Yes.
Yes, and like this only they will give in the gate paper. For example, they will give you a given they will give you a certain loading for a beam, and they will ask you what is the shape of the shear force diagram and the bending moment diagram. So during that time, you can actually use this concept like slope concept. Like for example, if the load intensity is constant, then the slope of the shear force diagram is actually constant. Okay, when the load intensity actually reduces, for example, in or varies, for example like this, then the slope of shear force diagram from A to B or B to C, okay, it actually reduces from B to C. Okay, and this should be a parabola. Okay, because the slope continuously changing because the loading at each cross section changes. Okay, and again at a wxx the slope is actually the loading diagram is actually increasing from B to C. Okay, then also here the slope is should actually increase. Okay, and here also it should be a parabola because at each cross section the loading actually changes. Okay, based on all these three things you can actually use the you can actually draw the shear force diagram. Okay, now coming to the bending moment diagram. Can anyone say how will be the bending moment diagram will look like, or what will be the bending moment at point A?
Negative.
Yeah, it is negative because it is left hand side and it is which direction?
Anti-clockwise.
Anti-clockwise direction. Yeah, and its magnitude is W small w L square by 2. Okay, and what will be the bending moment at point B?
0.
Yes. Yeah, bending moment at point B is actually 0. Okay, so this is point B. And what will be the variation of bending moment diagram from point A to point B?
Decreasing parabola.
Yes, decreasing parabola, because shear force is decreasing. Okay, shear force is decreasing from A to B, so therefore the slope of the bending moment should also decrease from A to B. Like this it should be. Okay, maybe you can draw the diagram very clearly. Okay, if I draw like this means then it's a increasing parabola. Okay, but here we need a decreasing parabola because shear force actually decreases. You can say dm by dx is decreasing, or the slope of the bending moment diagram is decreasing. Okay, so for this you can, and then for example to this particular problem, if they are asking what is the shear force, okay, shear force is equals to what at x is equals to, let's say let L is equals to 5 meters, okay, and at x is equals to 2 meters, what is the shear force value from A? Then what you will do at this point?
Using similar triangle approach.
Equation.
Yeah, equation would be better, because if you are using similar triangle, okay, then here it will be 2.5. Yeah, similar triangle also you can use. Yes, using similar triangles also you can find out, or else using the equation also you can find out. Okay, is it clear? When we are using similar triangles, when we are using equations, and when we are actually going for directly the slope concept, everything. Okay.
So actually, the similar triangle and equations are very similar.
Yes. See, actually, similar triangles means like you don't need to find out what is the equation. Okay, directly you can go to this diagram, and then you can find out. Okay, let this be WL, for example, if it is some value, and then you will know what is the length of this. Okay, for example, here I have given 5, right, and here also it will be 2.5, and then from similar triangles you can actually find out what is the length of this. Okay.
Yes.
Yeah, and if you are going for equation also, that is also fine, but both are different actually. And based on this equation only you are actually getting this linear curve, that is true. Okay, and when you are actually finding out the equation for the shear force, it will be actually in terms of x, which means like it is a straight line with a constant slope. Okay, and when you are finding out the bending moment equation, it will be some parabola, okay, in terms of x square. And when I have the shear force itself in terms of x square, then I will have the bending moment equation in terms of x cube. Okay.
Yes.
Yes. So can we stop here, or can we look at one more problem and then we shall stop?
Stop, sir.
Okay then. Okay. So I will be giving you some homework problems. I will be uploading in the PPT. Okay, you can download the PPT, and then all the drawings will be visible. Okay, by tomorrow, within tomorrow night, I will upload all the homework problems. Okay.
Excuse me, sir.
Yes.
Share drive link, sir.
Drive link. Okay, I will share you the drive link.
Sir, the video is available offline video recording.
Yes, I will upload the video also within today night. Okay.
Yeah, you can access in drive link only, sir.
Yes, I will
Video.
upload. Yes, I will upload the video and drive link only. Okay.
Thank you, sir.
Okay.
Excuse me, sir.
Yes.
Sir, can you please give this question which you are about to do as homework, sir, so that we can try?
Okay. Yeah, I will. 1 minute. First, I will save this. I will give you the problem, okay, as homework. Yes, you can note down this question. Okay. This is a fixed one end. It's a cantilever beam. Okay. This is the simple problem. Maybe you can find out the equations also for bending moment as well as shear force. Okay. And then you can draw the bending moment diagram and the shear force diagram. And this is of length L. And this is point A. This is point B. Okay. And this edge is W Newton per meter. Okay. Draw the shear force diagram and bending moment diagram, as well as find out the equations. Okay.
Okay.
Yeah. Maybe you can note down another one problem also. I will also give the same problems in the homework also. Okay. Similar here. Only thing is like here it will be inverted. Okay. And you can see what is the variation. Okay. Here itself point B stops. Okay. And here this is actually W Newton per meter. Okay. This is point A, same length L, everything. Okay.
Yes.
Yeah. This you can note down. And for all these things, you can find out the shear force at any cross section XX, as well as the bending moment at any cross section XX. Shall I close the presentation or?
So drive,
Yeah.
so drive link, sir.
Yeah, drive link I will share it. No.
Sir, bending moment is always zero at the free end.
Yeah, at the free end bending moment will always be zero until and unless you are having a concentrated moment at the point B. Okay.
Okay.
Yeah. I'll stop presenting. Okay. I will copy the drive link once again. I will share the drive link, okay, in the chat box.
Sir, this one related to
Your voice is breaking. I couldn't hear you properly. Hello?
hello.
Yes. Hello, Suraj. Your voice is actually breaking, so I couldn't hear you properly. Hello? Can you type your question in the chat box so that I will answer your question?
Now, am I audible, sir?
Yes, now you are audible. Yeah.
I was asking that there was one problem related to finding reactions that supports a
Yes,
vertical
yes.
by
Yeah,
mill
you have
and
mailed me,
the-
right? You have mailed me, right?
Yes, sir.
Yeah, I will solve that problem, and within tomorrow I will send you. Okay.
Okay, sir.
Yeah.
Thank you,
So
sir.
yeah, what is the feedback about today's class? Is everything fine or?
Yes, sir. Yes, sir.
Okay.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank Thank you.